Let us start the session. Good afternoon, everyone, and welcome to the session post lunch. So, this session will be taken by Dr. Shrikant Bonta. So, Dr. Shrikant Bonta is an associate professor at the Department of Mechanical Engineering, NIT Surathkal. He works on laser additive manufacturing process. Mostly, his work will be related to the computational modeling of the manufacturing process, which are related to laser-based process actually. So he will be talking about the what we can say is that mathematical how to model the laser based additive manufacturing process. So some of the few things which you have seen in the earlier session with Dr. Ramesh Singh, but they are very preliminary. So he will be talking more about what are the various methodologies which are being used to mathematically model the process. And Dr. Shrikant Banta, you can say hello to the participants first, then
Yeah, thank
okay.
you, Professor Gupta. Thank you very much. And I'll share my
And
video.
you have 1 hour 30 minutes.
Okay.
So 1 hour 15 minutes you can talk about your work, and maybe 15-20 minutes we can give time for the questionnaire actually.
Yeah, sure.
So let us welcome the speaker, and I wish you will be having a wonderful interaction with Dr. Shrikant actually. Thank you, Dr. Shrikant. So I made you a co-host. You can start actually.
So, Professor Gupta, should I share my video and start the presentation?
You can start actually. You are.
Yeah, okay, sure. Yeah. So, good afternoon to all the participants. First and foremost, I would like to thank Professor Gupta and the organizing team of Metal Additive Manufacturing MAM 2021 for giving me this opportunity to share my work in the area of metal additive manufacturing. So, I will share my screen. I hope all of you are able to see the screen.
Yes, sir.
Yeah, thank you very much. So my talk is titled as Computational Modeling of Laser Additive Manufacturing Process. So these are some of the sources for the content of this presentation. So I'll be dividing my talk as follows. I'll first briefly introduce to laser additive manufacturing because I know that there was a session in the morning on metal additive manufacturing process in general. Then I'll discuss about the complexity of this laser additive manufacturing, or LAM that we call them in short. I'll then discuss about the need for computational modeling of the LAM process. Then what are the challenges that we face when you're trying to model these processes. Then I'll be discussing about analytical modeling, followed by thermomechanical financial modeling, which is the numerical modeling of the LAM process. Then I'm going to show some case studies that illustrate the use of computational modeling to understand the characteristics of the deposit in the LAM process. And then I'll summarize my talk. So as you all know, and has been discussed in the earlier sessions, like in any additive manufacturing process, you start with 3D CAD model and you slice that into 2D cross-sectional layers. And particularly in particular laser additive manufacturing, what we do is we use a high energy density heat source as a laser to melt the powder, okay, and then deposit the material layer by layer to form the object. Now, as we all know, additive manufacturing is continuously evolving. So now there are also processes where you can use wire as a feedstock material. Not only powder, but wire also can be used as a feedstock material. So this additive manufacturing process have essentially evolved from rapid prototyping, and these have been developed over the past 3 decades, fabricating complex parts in a fast, flexible, and automatic manner, alleviating the need for any tooling. Now, all the additive manufacturing in the metal AM process, they share a similar characteristic. That is, they have a hierarchy. They start with a bead. Multiple beads will lead to a track. Multiple tracks will lead to a layer, and multiple leads will lead to a part. That's a hierarchy in metal AM. So I'm just illustrating that. So multiple beads, when you deposit them, they lead to a track. Multiple tracks will lead to a layer, and multiple layers lead to a part. Okay, so this is the hierarchy. So now there are two most widely used laser-based additive manufacturing process. One is the laser directed energy deposition process, which is also referred to as LDED. The second is laser powder bed fusion process, which is referred as LPBF. In the laser directed energy deposition or LDED process, you have a high power laser beam which is focused onto a metallic substrate where it creates a molten pool, and streams of metallic powder are simultaneously injected. Streams of metallic powder simultaneously injected to nozzles into the molten pool that is created by the laser beam, and as the table beneath the substrate is traversed in X and Y direction, or by moving the deposit head in X and Y direction, we deposit one layer of material. And to deposit the next layer of material, the focusing lens assembly and the laser are incremented in the positive Z direction. So in this way, the part is built line by line and layer by layer. So here you have a high power laser beam. Streams of metallic powder are simultaneously injected to the nozzles and into the molten pool. And this powder is carried by carrier gas. And the process generally takes place in an inert atmosphere organ to prevent oxidation of the molten metal. Okay, so this is generally referred to as a powder fed process. We are feeding the powder. Okay, so you have a substrate on which you create the deposit. Now, the other type of laser additive manufacturing process is the LPBF process, laser powder bed fusion process, where you have a powder bed. Okay, here you have a powder dispenser platform. Okay, and the metal powder is spread on the bed using a rake or a roller or a recoater arm, and then after spreading the powder on the bed, the powder is selectively scanned by using a laser. The laser selectively scans, and this scan takes place by use of an XY mirror. Okay, and the laser selectively scans regions of the powder bed based on the CAD model, based on the toolpath generated from the CAD model. And once the scanning of one layer is done, the build platform is lowered, the powder dispenser platform is raised, the next layer of powder is spread, and then the scanning takes place once again. In this way, again, you build the part line by line and layer by layer. So this is called a powder bed process, whereas the LDED is referred to as a powder fed process. Now, particularly, this presentation will more focus on the LDED process, that is the powder fed process. So both the technologies, right from the time of initial development, have proved beyond doubt that they can be very useful manufacturing techniques for low volume production. Okay, LDED is very much suited for repairing components because you can deposit material on any 3D surface, or you can add material to existing components, and you can also fabricate functionally graded structures. Okay, so LDED is most widely used for repairing components, for adding material to existing components, fabricating functional graded structures, whereas the laser powder bed fusion process is used for direct manufacturing components because you have better resolution, better surface finish with respect to the LPBF process compared to the LDED process. However, if you look at some of the obstacles to the widespread commercialization of these LAM techniques, the control of the melt pool size. As I said earlier, the multiple beads will lead to a track, and the bead is formed from a melt pool. So the control of melt pool size is required for consistency in the build conditions. The build conditions change depending upon the location of the deposition. Okay, then the other obstacle is residual stress. The control of residual stress is necessary to avoid tolerance loss and decrease reliability. Okay, and finally, the last important obstacle is to obtain consistent mechanical properties. As we all know, structure decides the mechanical properties. So control of microstructure becomes important to obtain a consistency of mechanical properties from the components deposited using LDED or LPBF process. Now, this figure illustrates the importance of consistency of the build conditions. So you can see these are several single tracks, that is, multiple beads that have led to the formation of a track. Several single tracks that have been deposited, and you can see that based on the process parameters, the tracks are of different width. Okay, and also you can clearly see that many of the tracks are inconsistent. In some tracks there is balling, that is the breaking of the molten metal into spheres, into small spherical spheres, that as you can see here, and this is reflected on the track here. And in some cases there's an inconsistent track. You have a larger dimensions of the track at one end compared to other end. For example, you can see this track which has larger dimensions at one end compared to the other end. So to obtain a consistent track, we need to optimize the process parameters to obtain a consistent track with no defects, okay, or minimal defects. So this illustrates the importance of consistency in the build conditions. Now, this figure illustrates the importance of the control of residual stress. You can clearly see here that a thin wall geometry is being deposited using the laser directed energy deposition process, and the sample is cracking during the deposition itself. This is because the residual stresses are exceeding the yield strength of the material. So it's very important to control the residual stress to avoid distortion, cracking, as well as the peeling off of the deposit from the substrate. Now, both these processes, laser directed energy deposition and laser powder bed fusion, are extremely complex in nature, because in these two techniques, several physical phenomena interact simultaneously. Not just in these two techniques, in general, in any metal layer, but since we are focusing on these two, so you have the interaction of several complex physical phenomena, such as you have heat transfer, okay? So you have conduction into the substrate, convection, radiation. There's a fluid flow within the molten pool, okay? Convective fluid flow, okay? You have melting taking place, the powder particles melting, the powder wire. Then you have solidification, you have solid state transformations, grain growth, diffusion. All of these physical phenomena are happening simultaneously that result in the extremely complex process, okay? Then several process variations are possible. Now, as you can, if you're aware, there are different LDED or LPPF machines in the market with different build envelope, different range of laser power, scanning speed, and so on. Especially in LDED, there are some machines that come with a maximum power of 1 kilowatt, whereas some machines go to 3 or 4 kilowatt. Okay, so and carry out the process in an open atmosphere for some materials, or you can need to carry out in an atmosphere, especially for titanium or titanium based alloys. Then there are large number of characteristics of the deposit that need to be understand, right? From build conditions, residual stress, microstructure, porosity. Okay, I list out some of the characteristics as we go further. And the complexity results from a large number of variables, both associated with the system as well as with the process. Okay, so all these large number of parameters make this process extremely complex. Then, as I said, the process parameters, I have only listed some of them here. Okay, the process parameters, they come from the laser, they come from the powder particles, okay, substrate, and so on. So if you look at some of the process parameters, you have power, scan speed. If it is DED, the powder flow rate, because powder is being fed. Then what is the hatch spacing, the layer thickness, the scan path, what's the temperature of the substrate, are we preheating or not, what is the inert gas flow rate. Okay, so and then on the other hand, you have powder. So what is the shape of the powder particles, what is the size and distribution of the powder particles, the chemical composition, okay, what is the flow bill, then the substrate is there, what's the composition of the substrate, okay, and then you have inert atmosphere of inert gas in both the process. So generally we tend to use argon or nitrogen. Argon is used for titanium alloys and all. Okay, so what is inert gas? Then you have a large number of deposit characteristics that need to be understood. For example, as I said, the melt pool is one of the most important one that determines the build conditions, and we need to look at the melt pool shape and melt pool dimensions. Then we need to look at defects such as porosity, which can come from the powder or from the process parameters. Okay, it can be gas porosity or lack of fusion porosity. Then we need to look at what kind of microstructure, the microstructure of the deposited component, the chemical composition, because sometimes there can be result of there can be a loss of allowing elements and all. Okay, so there are a large number of deposit characteristics that you may understood in terms of temperature, dimensions of melt pool, cooling rates, thermal gradients, residual stress, and all these important aspects. Okay, so if you look at the various inputs and outputs to these processes, so these are the inputs coming from the energy source. These are coming from the powder, the material, the feedstock from substrate. So you can see that there are a large number of process parameters. Okay, and in the deposition itself, you have melting, solidification, convective flows of the melt pool, interaction between powder and energy heat source. Okay, so there is a complex physical phenomena occurring the deposition itself. And there are a large number of deposit characteristics that need to be understood. Just some of them I've listed in the previous. So summarizing everything together, you have a large number of deposit process parameters. Okay, there's a complex interaction between different physical phenomena taking place at the time of deposition, and you have a large number of deposit characteristics that need to be understood. So one of the important concerns in metal additive manufacturing is that of part quality. Now, when you compare this metal additive manufacturing or laser additive manufacturing techniques to standard conventional manufacturing process, one thing becomes obvious is that this AM has not yet completely established standards for qualification certification of the process of the AM process. This is because of the complex combination of machines, materials, and processes and techniques. So the absence of a reliable database, what happens is it reduces the confidence of the OEM to adopt additive manufacturing process or fabrication of critical components in industries, aerospace, biomedical, automobile, and so on. So, and also the additive manufacturing process, as we spoke, are very challenging in terms of the large number of process parameters, the complex physical phenomena that takes place during deposition, as well as the number of deposit characteristics that need to be understood. In addition to this, the AM also has multiple length and time scales that are involved. Just to give an example, talk about this length and time scales in a coming slide here. Okay, so now if you look at part qualification, the traditional approach for part qualification is generally is expensive and it involves experimentation, which is both expensive and time consuming. Okay, so you need to do a large number of tests to create a reliable database, which can take a months to years to complete and may cost a significant amount of money. Further, as we have said, in additive manufacturing, machines and materials, they further complicate the qualification procedures. Therefore, a computational modeling is expected to play a vital role in the qualification of parts that are produced by additive manufacturing process. Now, one of the main goals of computational modeling is to reduce the experimental trial and error method that is generally used to optimize process parameters. And this optimization process parameters experimentally takes place. It needs a lot of time and it involves a significant amount of money. So one of the primary goals of computational modeling is to reduce the experimental trial and error optimization of the process parameters. So this modeling and simulation of LAM process can help us in better understanding of the process physics, thereby help us in producing parts with optimized build conditions, reduced tolerance loss because of residual stress, and better and consistent mechanical properties by control of microstructure. Now, in many cases, there are, for example, process output characteristics that are difficult to measure, or it may be challenging to measure experimentally, such as maximum temperature, the distribution of temperature, cooling rates, gradients, and so on. So modeling can provide a better understanding of this kind of parameters, okay, and also enable to predict them. And we can use modeling and simulation as a facilitating tool to understand the effect of process variables on the quality of the deposit. And this will help us to alleviate the need for extensive experimentation. So now I've just highlighted the importance of the need for computational modeling. But as I said earlier, metal AM processes are extremely complex in nature. So naturally, modeling of this process is also going to be challenging. So what are the challenges in the computational modeling of LAM process? I have listed some of them here. They may not be comprehensive. Okay. The first and foremost challenge is modeling the addition of material, because additive manufacturing is a layer by layer process. You're going to add material line by line and layer by layer. So how do you account for the addition of material in this process? If you look at additive manufacturing, you can think it of as a multi-pass welding. Okay. So the question that comes to mind is, how do we take into account the addition of material in AM process? The next challenge is you use a high energy density heat source in additive manufacturing. The most common ones being a laser or an electron beam if you are looking at the electron beam melting process. So how do we model the heat input coming from this high energy density heat source? Then as this high energy density heat source melts the powder particles and the powder particles solidify, how do you account for the thermal losses that take place during deposition? Accurately account for them. So what is the main mechanism of dissipation of heat, and how do you account for the thermal losses? Okay. Next thing is we know that the parts in AM undergo a very complex thermal cycling during deposition. That is, when you are depositing a current layer, the previous layers are heated and cooled. So this leads to the evolution of residual stresses. And to predict residual stresses, we should be able to accurately model the elastoplastic stresses and strains. And now, prediction of residual stress needs a thermomechanical simulation, not just a transient thermal, but a thermomechanical simulation. So the question that is, how do we couple this thermal and mechanical behavior in a manageable way? Okay, and then as we know, when you are heating the powder particles, the powder is initially to room temperature, it then melts and then solidifies. So there is a variation in the properties, the thermophysical properties with respect to temperature. So how do you account for the variation of the material properties of the feedstock material from room temperature to melting? Okay, and then how do we account for the multitude of complex physical phenomena that take place during AM? As I mentioned, all of these before: heat transfer, fluid mechanics, melting, solidification. Now, how much of the physical phenomena we are trying to capture in the computational models will determine the complexity of the model. The more physical phenomena we are trying to capture, that increases the complexity of the computational model. Now, I'm just going to give an example here. This example is basically about the length and time scales that I had briefly alluded to in one of my earlier slides. As I said, modeling and simulation of LAM process involves different length and time scales. Let's try to understand what this is. Let's take the case of the directed density deposition process. Here, the powder particles, the particle size is in the order of 50 to 150 microns. Okay, the size of the spot size of the laser beam is in the order of 0.5 to 2 or 4 mm. Some depends on the maximum power also. The dimensions of the workpiece are in the order of a few cubic centimeters to cubic meters. Now, particle melting occurs in a microsecond. Okay, a single scan, like a single track, takes a few seconds, and the build times can be anywhere from a few hours to several weeks. So you can clearly see that there are different length and different time scales involved in the LAM process. Now, for example, to simulate a build height of about 100 millimeters with a layer thickness of about 20 microns, which results in about 5,000 layers, the build time, actual build time, is about 20 hours. But the estimated computational time is several days with GPU machines. Okay, so this tells you the complexity of the computational modeling. Okay, so one of the greater challenges of the computational modeling is linked to completing the simulations in a useful time frame. Okay, that is the biggest challenge currently with the simulations, simulating the AM process. See, the whole idea of simulations is that we want to complete a large number of simulations to arrive at optimum processing conditions before we deposit the first part in a certain material and its geometry that's given to us. So for this to happen, the simulations must be completed in a small fraction of the build time. But as I mentioned, the simulations are taking a large amount of time. And if the simulation time is too long, if they take weeks or months to run, then what happens is that the usefulness of the simulation studies will be questioned, and the cost of experimental trial and the approach for optimizing process parameters may be accepted. So the greatest challenge that one faces with increasing the awareness or increasing the usage of computational modeling for AM process is completing the simulations in a useful time frame. Now, I'm going to discuss all the challenges now in great detail. Okay, so first challenge that I had mentioned to you was modeling the addition of material. So how do we account for the addition of material in additive manufacturing process? The first, as I said, when you are trying to addition of new material in the numerical model implies that you are adding new equations. Okay, so generally, when people started looking at modeling of AM process, they went back to welding, because we can think of additive manufacturing as multi-pass welding. And they started using a technique known as the element birth and death technique. Now, what happens here is that in the element birth and death technique, we start with a complete model of the geometry to be simulated. Okay, so the complete model is present at the start of the simulation. Now, what happens is that we then use something called element deathing or killing the elements. Okay, to remove the elements that are not yet deposited. Okay. So I'll just show an illustration to better explain that. Okay. So here we have different types of elements. We have what are known as activated elements and deactivated elements. And how do we deactivate an element? We deactivate an element by multiplying the thermophysical properties of the element, such as the specific heat or thermal conductivity, with a severe reduction factor. Okay. So before I just talk about that, so what we are doing here, we are taking the conductivity of the material, multiplying with a severe reduction factor of about 10 raised to minus 6, and assigning that value of conductivity to the inactive elements. The same thing we can do for the specific heat too. We can multiply with the severe reduction factor. So in the element birth and technique, we have three different types of elements. One is called active element, one is called inactive element, and the third one is activated element. Okay. Now, what is the difference between these three? I will highlight in the next slide. But before I go there, active elements and the activated elements are the only ones that will contribute to the global matrices in the finite element system of equations. That is very important to understand. Okay. Inactive elements, they are visually present in the model, but they do not contribute to the global system of equations, because what we have done, we have multiplied the thermophysical properties with a severe reduction factor, such as on the order of 10 raised to minus 6. Now, if you see here, for this illustration here, okay, this shows the deposition of the simulation of a thin wall geometry on a substrate. So here you have the substrate, and this is the thin wall geometry, the thin wall geometry. The simulation of thin wall geometry is occurring here. So here you can see that this heat source is currently at this location. Okay, so this is the element that's being activated. Okay, now the heat source moved from here to here, and it has also moved. It has moved from the previous layers. These layers have been deposited. So all these are active elements. These are also active elements. This element is currently being activated. These are all inactive elements. So active and activated elements are the only ones that will contribute to the global matrices in the finite element system of equations. Inactive elements do not contribute. Okay. So for example, if I have to do this, if I have to simulate the buildup of the simulation of thin wall, so I start with the substrate. I'm putting the first bead, is the first bead here. Okay. In step 1, then this is the location of the laser. Step 2, this is the location of the laser beam. Step 3, this is the location of the laser beam. So what I'm doing, I'm activating the elements based on the location of the laser. Okay. So these are the active elements. Next step, I'm going to activate the next element to the right here. That will be the activated element, and other elements are inactive. But when the simulation starts, all the elements are physically or visually present in the model. They are simply inactivated. So important to note that the inactive elements, they're not removed from the model. Okay. They are, and how can they be activated once again? They can be activated once again by reassigning their original material properties, by reassigning their thermophysical properties back. Okay. So when we are implementing this EBD or element birth and death technique, all the elements must be created in the pre-processing stage itself. Okay. And then, so initially we kill all the elements except that of the substrate. And then as the deposition occurs, we keep activating the elements based on the location of the heat source. Okay. So the next one is, how do we capture the input from the heat source? So when the first metallurgical process were developed, and to understand the effect of process parameters and the characteristics of the deposit, people visited the literature to understand what are the different types of modeling techniques that are available. And they particularly went back to the welding literature, because metal AM is nothing but multi-pass welding. So the first generation of heat source models, they essentially used analytical methods to calculate the thermal history. The examples of first generation of heat source models include that of Rosenthal solution, the Reichlin solution, and so on. The Rosenthal solution was given in the year 1946 for both point heat source, line heat source, and so on. Okay. Now, we all know that the analytical methods, they provide exact solutions for simple geometry domains, and they come with a lot of assumptions. Okay, I'll discuss the assumptions of the Rosenthal solution a little later. Okay, so the analytical methods they provide exact solution for simple geometric domains, and they can give an accurate prediction of temperature far away from the melt pool, especially when you have a point heat source model. Generally, the analytical methods, the temperature variation of material properties such as density, specific heat, thermal conductivity, they're all ignored. And the phase change effect is also ignored. That is, latent heat of phase change is not taken into account. Okay. So the first generation of heat source models that I've just discussed, the Rosenthal solution and Raiklin solution, they're only able to determine the steady state temperature field in welding. Now, these heat source models, when they are applied for AM, we need to understand that they may not be capable of simulating the transient temperature field of the melt pool in the AM process. Now, with improvements, the second generation heat source models, they started using the first generation heat source models, they used a point heat source. Okay, the second generation heat source models, they used a distributed heat flux model to capture the heat from the high energy density heat source. So they used either a 2D heat flux or a 3D volumetric heat source. Okay, so the second generation heat flux models are widely now used in the modeling of AM process, where the heat source can either be a laser or an electron beam. Now, the 2D Gaussian distributed heat flux has been the most widely used for modeling of the laser additive manufacturing process due to the small penetration depth of the laser beam. So this is one of the most widely used mathematical equation to model the heat input from the heat source, where here is F is applied heat flux. Now Q is the laser power, alpha is the energy absorption quotient that will change from material to material. Okay, R is the spot size of the laser beam. X and Y are the variables which will specify the distance from the laser center of the laser beam. So we have a Gaussian distribution here, and in general, the surface heat flux has been represented with different mathematical models for the 2D heat flux itself. Okay, and when you go for a volumetric flux, we also consider optical penetration depth. Now, one of the most important parameters when we are doing the computational modeling is the laser absorption quotient alpha, because this will change from material to material, and not only that, it will change it will also depend upon the laser beam that's used. Okay, so in fact, the laser absorption quotient is a very complex parameter that depends on several parameters, right from material. It also depends on surface roughness. It also depends on if oxide films are formed on the surface, the wavelength of the laser beam, the angle of incidence, the time of interaction, okay, the powder particle size and distribution, and the spot size and profile. So as you can clearly see, the absorption quotient is a very complex parameter that depends upon a host of parameters starting from material to the wavelength. Okay, and this is one of the important parameters that we need to include in the computational models. So in addition to the heat source models that I just mentioned, there are other heat source models that take into account the effects such as convective flows within the melt pool that are caused because of either buoyancy or surface tension gradient. Okay. Now, we know that convective flows occur in the molten pool because of density differences, because of electric current when you have when you're looking at electron beam process, and also because of the surface tension gradient. Now, Marangoni convection in the melt pool has been widely accepted to be the major driving force of fluid flow in the molten pool, and this Marangoni convection, it plays a very important role in determining the shape of the molten pool. I'm going to show an illustration as to how the temperature quotient of surface tension influences the shape of the molten pool. Okay. Now, the fluid flow and the heat transfer, they're very important in determining the size and shape of the molten pool, as well as not only the size and shape, but also the kind of microstructure that forms. Now, in the early days of LAM simulation, the fluid dynamics effects were neglected because when you want to consider these effects, or when you want to incorporate this physics into the computational models, you need to determine, you need to have additional quotient values, or you may have difficulties in obtaining solutions, mathematical difficulties in obtaining solutions. So researchers have generally tended to neglect some of these effects, such as the fluid dynamics in the molten pool. Now, as I said, if you're looking at the driving force of fluid flow in the molten pool, It can occur because of buoyancy, it can be the Lorentz force, or it can be because of the shear stress induced by the surface tension gradient at the molten pool surface. Now let's look at each one briefly. I'm not going to discuss about the Lorentz force because it's an electromagnetic force which results from electric current, and in the case of laser we don't have the Lorentz force coming into picture. So I'll be discussing about the buoyancy force and the Marangoni convection. So we know that the buoyancy force comes into picture because when you have a molten pool, or we can also call it as a weld pool, okay. Now this is the region where you have the material in molten state, okay. Now the density of the liquid metal, it decreases with increasing temperature, okay. Now the heat source is just above point A. Point B is close to the boundary of the molten pool. Since the heat source is above point A will be hotter than point B, okay. So the temperature at point B is lower than temperature at point A, okay. So naturally, the density of the molten metal at point B will be higher than the density of the molten metal at point A. Therefore, gravity will cause the heavier liquid metal at point B to sink. Consequently, the liquid metal will fall along the pool boundary and will rise along the pool axis. This is because of the buoyancy force. Then you have the surface tension gradient, okay. Now, the surface tension of when we don't have any surface active elements such as sulfur, oxygen, selenium, which have a tendency to flow to the surface of the molten metal, the surface tension of the liquid metal, it decreases with increasing temperature. That is, dou gamma by dou T is less than 0. Okay. So if you look here again, if you consider point A and point B in the weld pool or the molten pool, point A is at higher temperature, okay, and point B is at lower temperature. Surface tension decreases with increasing temperature. Okay, so now what happens? The warmer liquid metal with lower surface tension coefficient. So you have point A is at a higher temperature and the surface tension is lower at point A compared to that at point B. So this warmer liquid metal with low surface tension at point A, this is pulled in the outward direction by the cooler liquid metal with a higher coefficient of surface tension at point B. So what we can think of is there's an outward shear stress that is induced at the surface of the molten pool by the surface tension gradient along the pool surface. And this will cause the liquid metal to flow from the center towards the pool surface and then return beneath the pool surface. You can see that the liquid metal flows from the center towards the pool boundary and then flows back beneath the pool surface. The surface tension driven convection is also called as Marangoni convection or thermocapillary convection. Now, there are many situations when you have we have surface active elements in the melt pool. Surface active elements are such as the ones like sulfur, oxygen, selenium, tellurium, and all. These have a tendency to move to the surface of the molten pool. Now, when the surface active element is present in a small but significant amount, the sign of the temperature coefficient of surface tension changes, and thereby reversing the Marangoni convection. Okay. Now let's look at an example here. Okay. These are two welds. Okay. In 304 stainless steel. This is the case where the concentration of sulfur is 40 ppm, and it's a low concentration of sulfur. And this is the case when the concentration of sulfur is 140 ppm. So you can clearly see that at very low concentration of surface active element, the molten pool is shallow and wide. At high concentration of surface active element, the molten pool is narrow but deep. Okay, so this clearly shows the influence of the surface active elements on the direction of Marangoni convection. So here, so if you see again, as I show here, when you have low concentration of surface active element, okay, what happens is that you have the warmer liquid metal of low surface tension near the center of the pool surface. This is pulled outward by the cooler liquid metal of higher surface tension. So essentially, here in this case, the dou gamma by dou T is less than 0. So you have the warmer liquid metal of low surface tension being pulled towards the boundary of the pool, where you have cooler liquid metal of higher surface tension. But in the other way around, when you have a surface active element, what happens is that the sign of d gamma by dt changes, and the cooler liquid metal of lower surface tension at the pool surface is pulled inward by the warmer liquid metal of high surface tension at the center of the pool. So what happens? Now in this case, you have the convective flow from the edge to the center, and the convective heat transfer from the heat source to the bottom. So the liquid metal in this case carries the heat from the heat source to the pool bottom more effectively. Thereby, the depth of the molten pool increases, and the molten pool is narrow but deep. So this is about the different heat source models, the first generation heat source models, second generation heat source models, and other heat source models that take into account the effects of fluid dynamics and so on. Okay. Now I'll be talking about the heat transfer. How do you model the heat transfer during laser additive manufacturing process? We all know that in laser additive manufacturing, we create a part by consolidating the material, that is adding material layer by layer. Okay. Now, how is this consolidation takes place? This consolidation takes place by melting and upon solidification. Okay. So the feedstock is irradiated by a high density heat source such as a laser or an electron beam. Okay. It melts it, and then through solidification, the deposit is built. Now, the energy that is used to melt the material. Okay. Now, if you look at that partitioning and you write the energy balance equation across system, the energy can be written as follows. So Q with the subscript L is the heat flux from the heat source. Okay. Now this heat flux is equivalent to QCD, where this is the heat lost due to conduction. Okay. QCV is the heat loss due to convection, and QR is the heat loss due to radiation. Now, it has been shown in additive manufacturing in metal AM process that conduction is the dominant mode of heat transfer, conduction through the substrate. Okay. And in the early days of simulation of LAM process, since conduction was the dominant mode of heat transfer, to reduce the complexity, the heat loss or dissipation of heat because of convection and radiation were neglected. However, with improvements in computational power and all, nowadays the researchers also take into account the heat losses due to convection and radiation, as well as the effects of convective flow in the molten pool. Now, the 3D heat, essentially when we are looking at the transient thermal analysis, we are solving the 3D heat conduction equation, which according to Fourier's law is given by this equation here. Okay, you have this is the 3D heat conduction equation. In this equation, K is the conductivity, thermal conductivity, T is the temperature, Q dot is the rate at which the heat is supplied to the system, Cp is specific heat, rho is the density, and small t is the time of interaction between the beam and the feedstock material. Now, as we know that in this metal AM process, we're going to have phase transformation, solid to liquid and liquid to solid. So the enthalpy change due to phase transformation needs to be taken into account. So we use that. For that is dH equal to Cp dt, and we plug it here. So the equation becomes, so you have rho dH per dt replaces the right hand term here. So when we include the enthalpy change, okay. So the initial conditions can be expressed as T is a T naught, that is the T naught is the initial temperature substrate. In some cases, we may want to preheat the substrate to minimize the thermal gradients and thereby the residual stress. In that case, we can put T equal to whatever is the temperature substrate, maybe 200, 300, or even higher. Okay. And the heat losses per convection and radiation, when they considered, the boundary conditions for the free surface of the part R can be represented as follows. This is the conduction, convection, and radiation. We need to understand that when we include convection and radiation, we need to know the convective heat transfer coefficient H, the emissivity. Okay, these parameters, the values of these parameters need to be known. Okay. Okay. Now moving on. In additive manufacturing process, essentially what happens is that the temperature causes the mechanical response. Okay, so we are essentially melting the powder by using a high intensity heat source, and because of thermal cycling, you have a evolution of stress. So temperature is causing the mechanical response. Okay, so generally the simulation of the entire deposition can be broken into can be looked at in two different ways. Okay, that is, you can take the thermomechanical analysis and you can break it into two. One is the transient thermal analysis, the other one is the mechanical analysis. Okay, now generally what happens is, for reducing the complexity, each analysis, that's thermal and mechanical, they can be treated separately. So this is where one thing that becomes important is that, are we coupling the analysis or are we uncoupling the analysis? That will determine the complexity of the simulation. Okay, that's why I'm discussing about coupling the thermomechanical behavior. Let's try to understand what's the difference between a coupled and uncoupled analysis. As I said just now, the temperature causes the mechanical response in EM. Okay, now once the stresses exceed the yield strength, there's going to be plastic deformation that is converted to heat. Okay, now whether we take into account this heat generation into the computation of the temperature field is what decides whether it's a coupled or uncoupled analysis. So we have the thermal analysis on the mechanical analysis. You can do a coupled analysis or you can do an uncoupled analysis. So what happens in uncoupled? In uncoupled, the situation is like the upstream affects the downstream. That is, thermal analysis affects the mechanical analysis, but not vice versa. In coupled analysis, upstream affects downstream and downstream affects upstream. Let me explain to you what I mean by that. Okay, so what happens is that in the coupled analysis, the heat generation that's caused by friction, that is plastic deformation, that will be considered in the calculation of the temperature field. So basically, the temperature is causing the stress, and the heat generation because of plastic deformation, that is used in the calculation of the temperature field. So it is coupled analysis. Okay, so if you want to take this into account, both thermal and mechanical analysis, they have to be performed simultaneously. Okay, we first do the thermal analysis and then we do the mechanical analysis in the same step. Okay, so we solve it, so it increases the number of equations that need to be solved in each time step. Now, in the case of uncoupled analysis, as the name suggests, it's performed sequentially. That is, upstream affects downstream, but downstream does not affect upstream. That is, thermal analysis affects the mechanical analysis, but mechanical does not affect the thermal analysis. So what happens is that there is the interaction between the stress and temperature fields is not considered. So what we do in the uncoupled analysis is that the temperature field obtained from thermal analysis is applied as a load to structural analysis. Now, researchers have widely used uncoupled analysis in literature because it saves on computational time, even though there is some loss in the accuracy of the results from the simulation. So how do you do the uncoupled analysis? So here you can see that we first carry out the thermal analysis. Okay, we give the initial conditions, the boundary conditions, the loads, the heat flux, material properties, okay, such as density, specific heat, thermal conductivity, etc. Carry out the transient thermal analysis. Then the results are saved as a file called jobname.rth. RTH stands for results of thermal analysis. I'm specifically talking with respect to the commercial finite element software package ANSYS, but this procedure is similar to most of the commercial FEA packages. Once you save the results of thermal analysis, you apply this as a load in the structural analysis. You apply the temperature as a function of time at each node as a load in the structural analysis. So you solve the structural analysis by applying the boundary conditions, loads, and the material properties such as elastic modulus, thermal expansion coefficient, yield strength, and so on. And then once you carry out the structural analysis, you get a file called results jobname.rst, which is the results of structural analysis, which gives you information about the stress, magnitude and distribution of stress, and the displacement in the model. So I'm going to now discuss briefly about the analytical modeling of LAM process, and then discuss about the numerical modeling, and then present some case studies. So as I said, the first generation heat source models, they used the analytical models available in literature to predict the steady state temperature fields. So the Rosenthal solution that was given in 1946 for welding was widely used to calculate the thermal history. The Rosenthal is an analytical method. It neglects temperature. It makes several assumptions. One of the major assumptions is that it neglects the variation of properties as a function of temperature. It neglects the effect of exchange, that's latent heat. Okay. It also assumes that geometries are infinite or semi-infinite. That is, that the molten pool does not see the effects of the free edges. Okay. It also assumes that the heat source is a point heat source and the rate of heat input is constant. Okay. So this is a semi-infinite geometry, a thin wall geometry, and the Rosenthal solution for this geometry is given by this equation in non-dimensional form. So people have expressed the Rosenthal equation in non-dimensional form so that we can remove the effect of the actual dimensions. Okay. So here in this equation, K0 is a modified Bessel function of the second kind in order 0. And the dimensionless temperature is defined by this equation. The dimensionless spatial coordinates x and z are given by this equation. If you see here, this is the heat source. So you're going to have a molten pool here, and you have a coordinate system x0, z0 that moves to the molten pool, and a fixed coordinate system. Okay, so T is the temperature at the location relative to the moving heat source. Okay, T0 is the initial temperature of the wall. Rho Ck are the density specified in thermal conductivity. All of them are assumed to be constant. B is the wall thickness. Okay. So here, if you see in this equation, the normalization is carried out in terms of the material properties and the process parameters. Process parameters are absorbed laser power alpha Q and scan speed V. Okay. So this is the temperature normalization and this is the spatial normalization. So the advantage of analytical solution is that it is exact for simple domains, but it makes a number of assumptions. So here we can take this analytical solution and differentiate with respect to time to obtain the cooling rate equation and differentiate with respect to the spatial coordinates to get the thermal gradients. So this is the expression for dimensionless cooling rate and this is the expression for thermal gradients. Okay, and the dimensionless time is given by this equation. Now we want actual values of cooling rates, actual values of gradients, not the dimensionless values. So the relationship between the dimensionless and actual values is given by these equations here. Okay. Now, how do we calculate the cooling rates, thermal gradients, temperature, the molten pool? So if you have a molten pool that's as shown here, okay. So what happens here is that we calculate the coordinates that lie along the boundary of the molten pool, okay, by replacing the temperature T here with the melting temperature. When we replace the T with melting temperature, it indicates that the thermal contours represent a molten pool. We find out the coordinates x0 and z0 that lie along the boundary of the melt pool using a numerical root finding technique. It can be done using MATLAB. Once we find the coordinates, we can plug these coordinates back into the equations for cooling rates and gradients and determine the cooling rates and gradients. And not only that, we can also find the temperature and so on. So basically, now this slide here shows what are called process maps that have been developed for cooling rates and thermal gradients. This is for the semi-infinite thin wall geometry. So this process map is a 3D plot. Okay, you have dimensionless cooling rate on this axis here, which is plotted as a function of normalized melting temperature, that is the Tm bar, to the depth of the melt pool. So we are plotting the relative depth of the melt pool. So Z0 by Zr. So this is 0 means we are at the surface, 1 means we are at the bottom of the melt pool. Okay, we are normalizing the melt pool. So this is the dimensionless plot for cooling rate. This is the plot for thermal gradient. You can see that both cooling rates and thermal gradients, they change by several orders of magnitude with changes in laser power and scan speed. And this is more clearly seen when you plot them on a log scale. But compared to thermal gradient, cooling rate is more sensitive to depth when compared to thermal gradient. Now, the actual cooling rate scales with the square of the velocity as per the normalization here, and the actual gradient scales linearly with velocity. Later on, I'm going to show you how the information from these process maps can be used to make to obtain insights on the morphology of the grains that are obtained in the LAM process. So I'm going to discuss about numerical modeling now. As you can see here, I had shown you this picture earlier. The numerical modeling is broken into two different steps, thermal and mechanical analysis. But the workflow in each analysis is the same. We have pre-processing, solution, and post-processing. So if you look at thermal analysis, we are going to first import the geometry or create the geometry in the software. We're going to mesh it, okay? we need to determine the number of elements. I'm going to discuss the mesh very briefly, and then we need to apply the boundary conditions like convection radiation, the initial condition temperature, the heat flux, and the material properties that are used are density, specific heat, thermal conductivity, latent heat, convective heat transfer coefficient, and emissivity, and so on. We solve the heat conduction equation here, okay, and then the output of thermal analysis is that you get temperature field, the thermal field, okay. The mechanical analysis, again, the boundary conditions are going to be about displacement or rotation boundary conditions. We have initial conditions, that is zero displacement, we fix them. The load is a temperature field obtained from thermal analysis. The material properties are generally elastic modulus, Poisson's ratio, thermal expansion coefficient, yield strength, hardening model, and so on. Here we solve the equations of equilibrium, and the output is that of the nodal output is a displacement from which we compute the strains and the stresses. So these are the various steps in each of the pre-processing stage. We define the geometry, the material properties based on the type of analysis, we mesh it, we apply the initial conditions, boundary conditions, and then the loads. Now, as I said, the material properties that we define will vary in thermal analysis and the mechanical analysis. In thermal, we are looking at density, thermal conductivity, specific heat, and latent heat. In mechanical analysis, we are looking at elastic modulus, Poisson's ratio, yield strength, thermal expansion coefficient, hardening model. And most of these properties are defined as a function of temperature. Now, one of the important aspects in the numerical simulation is meshing. Okay. Now, we all know that the accuracy of simulation is affected by the size of the elements, the characteristics of the mesh. Okay. But as we decrease the size of the element, the computational time increases. So a popular technique among additive manufacturing simulation studies is to use the mesh density, which changes in different regions of the model. Now, we know that when in the region close to heat source, the thermal gradients are going to be steep. And an accurate analysis of the thermal gradients will require a dense mesh in these regions. But away from the heat source, the gradients are relatively constant. And we can coarsen the mesh when we are away from the heat source. So in regions close to the heat source, the mesh should be dense. Regions away from the heat source, the mesh should be coarse. But however, the problem is, as we are adding material, the heat source keeps moving. Therefore, we need to use an adaptive meshing to ensure that the regions near the heat source have a dense mesh, and regions away from the heat source, we can coarsen the mesh. Okay, and the substrate can be meshed with an element size that is larger than the underlying layers to reduce the simulation time. Further, as when we are depositing, say, layer number 10, the initial layers, layer 1, 2, 3, whose effect on layer 10 is now minimal, can be meshed with coarse mesh. Okay, and how do we take into account the addition of material? By using the element Bertrand technique. So once we finish the pre-processing stage, where we define the material type, we define the material, the boundary conditions, initial conditions, meshing, loads, we go to the solution stage. In the solution stage, the partial differential equations we have discussed, the 3D heat conduction equation or the equations of equilibrium, they are discretized into the equations for each element and then are assembled into a global system of equations. Okay. Now we know that the LAM process are highly nonlinear in nature because of the temperature dependent variation of properties as well as plasticity deformation. Okay. So due to the nonlinearity, the complexity of simulations increases. So the transient thermal analysis is represented by this global system of equations when you're solving it using the numerical method, where K is the thermal conductivity matrix, C is the specific heat matrix, this T is the vector of nodal temperature, T prime is the time derivative of T, V is the velocity vector, and this is 0 when there's no mass transport, and Q is the nodal heat flow vector. Now, once we solve the thermal problem, we need to solve the structural problem. So how do we do it? We have to replace the thermal element with an elastic plastic element, input the temperature versus time at each node as a load, and also use material properties for the structural analysis. So the nonlinear mechanical analysis problem is described by the following equation. This is the temperature dependent stiffness matrix, external load vector, the temperature load vector, and this is the displacement vector. Now, for each load step, the nodal temperatures from the thermal analysis, they're ready to the structural analysis. And the nodal temperatures from this are from thermal analysis, they're ready to structural analysis till the time when the temperature of the model reaches the ambient temperature. So this is a thin wall geometry, and this shows the simulation of the thin wall geometry. We need to understand that thin wall is a single track multi-layer. Okay, we have only one track in each layer. It's a single track multi-layer. So this shows the movement of the heat source as the material is being deposited. Then this is a plate geometry. This is multi-track, multi-layer deposit. So you have more than one track in each layer, and then you have subsequent many layers. So this shows the movement of the heat source across different tracks and different layers. Now, post-processing. What can we get from the finite element or the numerical models? We can obtain the dimensions of the molten pool. We can have information of the shape of the molten pool, the maximum temperature in the molten pool, the temperature distribution, the thermal cycling that each layer undergoes, the cooling rates, which determine the grain size, thermal gradients, which along with cooling rate will determine the grain morphology, the thermal stresses, strains, and so on. So I'm going to present some case studies that will show how numerical modeling has been used to understand the effect of process parameters on the quality of the deposit in metal AM. So the first case study is pertaining to effect of process variables on key deposit characteristics in LDED deposit I64. So what we have done is, this is a thin wall geometry that was fabricated. I'm going to show the thin wall geometry in the next slide, that was fabricated using LDED process. This is the ANSYS FEM model, and we have simulated about 102 layers. I'm just showing the first file, the temperature distribution of the first 5 layers. You can see that the size of the molten pool increases as the number of layers increase. This is because when you are depositing layer number 1, the substrate acts as a heat sink. Substrate is at room temperature generally. It acts as a heat sink and extracts the heat. But as the number of layers increases, the effect of substrate decreases and the size of the molten pool and the temperature increases. And this shows the effect of thermal cycling here. So let's look at the layer number 10. Okay, so this is the temperature distribution in layer number 10 when layer number 10 is being deposited. And this is the temperature distribution in layer number 10 when layer number 11 is being deposited, when layer number 12 is being deposited, and when layer number 13 is being deposited. You can clearly see that when we are depositing layer 11, layer 10 is also melted and it cools down. So you can see that when you deposit layer 12, layer 11 is heated almost close to melting temperature. This red line shows the melting temperature of I64, which is 1654 degrees Celsius. That's the liquidus temperature. So you can see that each layer undergoes a complex thermal history during the subsequent deposition also. So now this is the deposited thin wall geometry, and this is the FEM model. We have simulated the 102 layers, and these are the different processing parameters. And what we have done is the value of residual stress has been measured at a certain point along the deposit, and the residual stress was predicted from the numerical model at a similar point. And you can see that these are the simulation values of residual stress, and these are the measured values of residual stress at the same location along the thin wall. So you can clearly see that in some cases there is a good prediction between the simulation predicted residual stress results and experimentally measured residual stress results using XRD technique. Okay, in some cases there is some difference, but even then too the difference is, the error is not very high. Now, as I said, I have shown you these process maps for cooling rates and thermal gradients. These were generated using the analytical solution. So now I'll show you how these are used to make inferences on grain morphology. So we can take the information of cooling rates and gradients from the process maps or finite element numerical models and define a parameter called solidification velocity, which is nothing but the ratio of cooling rate to thermal gradient. And then we can plot them on what is called a G versus R space or a solidification map. These kind of solidification maps are available for some common materials like Ti6 or superalloys, Inconel 718, Inconel 625, and so on. Okay, so but again, one important thing is the process maps, the results were expressed in dimensionless form. So what we have done is we have converted them into actual values using the properties of the material at the liquidus temperature. So now what do you mean by grain morphology? I'm just showing an example here. This is what we know as equiaxed morphology. This is the cast Tyche-4. This is what was predicted. This is from a literature. This is not the work done by my research group. They have used cellular automaton finite element modeling to predict the grain morphology in LDD deposited Tyche-4. So this is the this is the cast Tyche-4 itself. This is the grain morphology in lens deposited Tyche-4. This is columnar morphology, long elongated grains, and this is the grain morphology predicted using the CA cellular automaton modeling technique, which shows a columnar morphology. Okay. So now, what I'm showing here is these are the results from finite element modeling. These are the results from analytical modeling, okay, Rosenthal solution, and these are the experimental results for the thin wall geometry. So what we have done is we have taken a case where we varied the power and kept the velocity constant. For all the powers and at same velocity, constant velocity, the data points through the depth of the molten pool indicate that a fully columnar microstructure will be formed. Now, if you see, this is G versus R. On the y-axis, we have thermal gradient. On the x-axis, you have solidification velocity, which is the ratio of cooling rate to thermal gradient. Okay, so the G versus R map will tell us whether the grain morphology will be columnar, mixed, or equiaxed. Okay, so it's showing that it's a fully columnar morphology. The Rosenthal solution, in spite of neglecting temperature variation of properties, latent heat and all, is predicting a fully columnar morphology, and the experimental results are also predicting a fully columnar morphology. So important takeaway from here is that the Rosenthal results can give insights into trends in the grain morphology, okay, even though they are making several assumptions. The advantage of the Rosenthal solution is that you can get the results in a matter of few minutes to hour compared to the FEM or the actual experiments, which can take days to look at the morphology. This is the case for a plate structure. Okay, this was done at Penn State for a 14 kilowatt laser beam. So you can see a mixed morphology, and this is the Rosenthal and FEM results showing from powers from 5 watt to 30 watt, 35 kilowatt to 30 kilowatt. In the early days of LDD process, there was a process from a company called Aeromet, which used an 18 kilowatt laser. Okay, so it used a very high laser power. So here, if you see, it is showing that it is possible to, for a graded microstructure through the depth of the deposit with a fully equiaxed at the surface and a columnar at the bottom and also a mixed microstructure. The Rosenthal results are in agreement with experimental observations as well as with the numerical modeling results. Now, the next one case study I'm going to show is prediction of residual stress in laser deposited Inconel 718. This we have compared our results with published literature. So this is a work by Debroy et al. In 2017. This is their model. They have simulated the deposition of a thin wall geometry. This is substrate, and this is the geometry. 10 layers, and we have done the same thing in the current work. 10 layers, and this shows the distribution of residual stress in the thin wall geometry along the build direction. What we have tried to do is we have tried to use the same contour scale so that it makes apples to apples comparison. And you can see that there is a good agreement in the trends. There is some discrepancy in the numbers, which can be attributed to the fact that in our work, we neglected the effect of fluid flow, whereas in the work that was published by Mr. Mukherjee et al., they included the effect of fluid flow. And when the effect of fluid flow is incorporated, cooling rate, the cooling rates predicted will be lower. Then we look at a multi-material system, prediction of residual stress in laser deposited H13 tool steel on a copper substrate. So here, in a work by Tushar et al., they looked at a situation where you have a different substrate and a different deposit here. You have a copper substrate on which you have deposited H13 steel using two different scanning strategies, alternative and unidirectional. Unidirectional, you go from left to right, the laser is then moves back to the left and again scans. So there is a dwell time here. The next one is you go from left to right and then come back from in the opposite direction. This is the alternative scan strategy. So here, what they've done is they have plotted the temperature cycling in substrate in the layer 1, layer 4, and this is our work where we have plotted the same. And you can see that the temperatures predicted from our work are in close agreement with that reported by Tushar et al. And even the thermal cycling is in very good agreement for both the scanning strategies. And then they've also predicted residual stress in the interface between the two materials. And this is the results from the work of Tushar et al. And this is from our work. You can see that the trend wise it's in agreement, whereas there is some discrepancy in the actual numbers. Then this case study shows the simulation of the laser powder bed fusion process for deposition of Ti-64 material. We have compared results with that published by Fu et al. In 2014. So this is the model of Fu et al. They have simulated the LPBF process. These are the processing conditions. Laser power is varying between 20 to 80 watts. Scanning speed at 200 mm per second. Spot size is about 26 microns. Thickness of layers is about 30 microns. So we have done the same thing here. You can see that the layer thickness is about 30 microns and a 2D surface heat flux. And the laser is modeled as a Gaussian heat source. So this shows what they've done is they have considered, since the LPBF process you have powder and the solid, they've considered the powder properties and solid properties, and they carried out simulations, and they've also done experimental measurements of the melt pool dimensions. So this is the melt pool width for only solid, for powder, and experimental results. And these are our results where, and you can see that our results are in good agreement with that predicted from the work of Fu et al. And this is the percentage error that you can see, and it's obvious that the percentage error is lower than 10%. So this is for the depth of the melt pool. Again, they plotted for solid, powder, and experimental work, and this is our results here. Again, you can see that these are good agreement that reported by Fu et al. And the percentage error is lower. And this study shows the effect of incorporating fluid dynamics effects. What we have done is we have done the simplest case, that is laser surface melting of internal 625. So this is we have taken we have used LPBF process to scan and remelt a wrought 625 plate. These are the remelted tracks. This is the melt pool cross section, and this is the model where we have used a Gaussian heat flux. The scanning direction, this is the boundary conditions. Convection boundary conditions applied in all the surfaces. Ambient temperature is taken as 298 and insulation at the bottom. So this shows the melt pool width plotted as a function of scan speed for different powers. So you can see that you have experimental data. We have also carried out actual deposition and measured the melt pool dimensions using microscopic techniques. And this is the solid line. This is the experimental results. This is the one with fluid flow, and this is without fluid flow. You can see that with fluid flow, the melt pool dimensions are in good agreement with that of experimental observations. Again, this is the melt pool width. Again, the same results are seen here. The with fluid flow shows better agreement compared to neglecting the fluid flow. Okay, and you can clearly see when we observe the melt pool shape prediction with fluid flow shows a better agreement with that shown by optical microscope compared to that neglecting the fluid flow. And this shows the predicted velocity fields from the model considering the fluid flow. Okay, so here we have the convection taking place from the boundary towards the center and the downward direction. So you have a narrow and deep molten pool. So we have also looked at the effect of temperature coefficient to surface tension. That's a positive value, negative value. So when we used a negative value, we had a shallow and wide molten pool. And when we used a positive value of temperature coefficient to surface tension, assuming the presence of surface active elements, then we have a deep and a narrow and deep pool. So to summarize the talk, this laser additive manufacturing processes such as laser powder bed fusion and direct image deposition, they are under consideration for several applications, in particular for aerospace applications, because of the increases in efficiency and flexibility when compared to conventional manufacturing process in terms of the buy-to-fly ratio, the lead time for production of components. But in the LAM process, either a single track, multi-layer or multi-track, multi-layer, the layers experience a complex thermal history in different regions of the build. The thermal history, it induces residual stress, and this is the main cause for cracking or distortion of the parts. And the management of residual stress and resulting distortion is very important for the widespread application of LAM process. In addition to residual stress, it's important to understand the build conditions and the microstructure for consistency in mechanical properties. So in this work, we have used analytical modeling and numerical modeling to understand the effect of process parameters on build conditions, residual stress, and microstructure. We have also used analytical modeling to develop process maps for cooling rates and thermal gradients. And then we have used the information to predict grain morphology for the Tysis 4 material system. And the grain morphology predicted from the Rosenthal solution was in agreement with that reported by FEM and experimental observations. So this concludes the presentation. Thank you all for your time and attention. I'm open for any questions.
Thank you, Dr. Srikanth, for an exhaustive and elaborative work which you have done on Ty6 actually. This you have used PBF, like powder bed only, or SLS?
The most of the work is reported with respect to the LDED process, that is the powder fed process.
Powder bed.
There's only powder fed, that is the LDED process, where you're feeding powder nozzles.
Okay, fine. Okay, LDED you are talking actually.
Yeah, most of the work that we have done is with respect to the LDED process.
Okay, fine. Now the participants, like, you can have like the questions you can ask actually. You are open for discussion.
Sir, am I audible?
Yeah, please go ahead.
Thanks. Actually, your presentation is great and it's nicer. So I have one doubt. In one slide, you compared thermal analysis of simulation and experimental.
Okay.
So in experimental case, you shown that the temperature rise to 2500. So when the material temperature, the depositing material temperature is in the range of 1600, 500, how it can go to 2500?
See, in the AM process, there is going to be situations where there's going to be loss of allowing elements because of evaporation also. Okay, so if you take some materials like Ty6 4, for example, the liquidation temperature is about 1654 or so on, but the temperatures can go as high as about 2300, 2400 degrees centigrade, and you may reach a situation where the low boiling point elements may evaporate. And this is especially the case in all the metal AM process. Therefore, one of the defects is the loss of alloying elements.
Okay, sir.
Sir, one question from my side. Is this coupled and uncoupled analysis in this deposition process? You finally states that coupled analysis is the more accurate than uncoupled analysis. Is it the final decision?
See, coupled analysis is more accurate because generally what happens is that when temperature response is causing the stress, there will be some plastic deformation when the yield stress when the stress in the material exceeds yield stress, and then there's going to be some heat generation. That heat generation is taken into calculation of temperature field in the coupled analysis. But the problem is in the coupled analysis, you have to solve both the equations, the heat conduction equation and the stress equilibrium equations in each time step. So that will be a lot of computational time. The computational time is much higher. Uncoupled, you are decoupling both of them. So you're solving the thermal analysis first and doing the mechanical analysis. So there is going to be some loss of accuracy. But uncoupled analysis is widely reported in literature, even though there is loss of accuracy, because you get trend-wise results which are in good agreement with that reported from experimental observations also. So uncoupled analysis, even though there is loss of accuracy, it is widely used because of the computational requirements.
But those results are acceptable. I mean, compared to experimental results.
Even the experimental, yeah. Sorry, please go ahead.
I'm asking, since computational efforts are more in coupled analysis, so uncoupled analysis results are widely acceptable when compared to the experimental results. What you are saying that?
See, it all depends on it. I don't want to make a general comment, but my observation of literature is that the uncoupled analysis has been most widely reported in literature. The reason is,
Simplicity.
there is a loss of accuracy. That is different, but simplicity. Because as I said in my earlier slides, if you are doing a simulation and the simulation goes for weeks or maybe days or weeks or even months, then the need for the simulation will be questioned. You are trying to look at ways to reduce the simulation time, and decoupling is one way. Okay,
Right,
so
sir.
if you are looking at trends in the results, I think uncoupled should be okay.
Okay, sir. Thank you. Thank you, sir.
Thank you.
Yeah, any other questions, please? Okay. Now, in the residual stresses, when you are measuring, you are using the same XRD technique only. Is there any other method?
We have used XRD technique only.
Okay, so you have that facility with you?
We have recently got the facility. Previously, we have used outside facility, but recently, yes, we have the XRD technique to measure residual stress.
So we were of the opinion of using this hole drilling method. Whether I don't know whether that is suitable for such applications or not. This like particularly these AM components.
See, I have never tried the technique. Yeah, so maybe I'm not very sure, but literature, XRD is one of the commonly used technique. They have also used other techniques like what you have mentioned, also neutron diffraction techniques by some researchers and all. But I've never used hole drilling.
Okay, fine. Yeah, any other questions, please? Fine. If you don't have any other questions, thank you, Dr. Srikanth, and let us give the speaker our thanks for sharing all the experiences on AM techniques, computational modeling specifically, where people are most of the times even people are stuck with such type of analysis actually. So you might be having a software, but you don't know what to implement and how to implement, what to get and what not to get. So, but this presentation will give some broad overview, what are the boundary conditions to be given and what is that you are going to look for it. So fine. Thank you, Dr. Srikanth, and for this wonderful session. And on behalf of all the participants, I thank you very much for this session. Thank you.
Thank you, Professor Gupta, and thank you to the organizers of this MAM 2021 and all the participants for that.
Thank you, sir. Thank you.
Thank you.
Thank you. Thank you.
Thank you.
So all the participants, you don't have to do any attendance. Attendance will be automatically, it will be generated. You don't have to worry. Okay, thank you for everyone, for all the participants. Tomorrow we will be having the 3 sessions. We'll start with Dr. Deepa Srinivasan, followed by Dr. Puneet Tandon, and the post lunch we'll be having our own research scholar Chaitanya will be talking on the various aspects. So for this today's session, I thank you everyone, and we can close the session for this today. Thank you everyone. Have a nice day.
Okay. Thank you, sir. Thank you, sir.